Okay, Assalamualaikum and good morning. So we continue our lecture. But,
Waalaikumsalam.
okay, so we have this example, and this example actually will show you the final answer of drag force and drag coefficient. So me now, our aim is to get the drag force and the drag coefficient. And from this example, I will show you how to get that from the von Karman equation and other parameters. Okay, let's say. So let's say we need to determine the boundary layer thickness and drag coefficient in laminar boundary layer that have polynomial velocity profile. Okay, so in next notes, I will show you how to prove the polynomial velocity profile. But for these notes, okay, we focus on how to get the boundary layer thickness and drag coefficient. So here, the boundary layer thickness, okay, as I said previously in our equation, we just write delta is equal y at u equal 0.99 capital U. So it means that this equation cannot be solved. It's too easy. It's straightforward. So it means that we need to use another equation to get the value of delta. Okay. So about the polynomial profile. So actually it is fixed. Polynomial profile of boundary layer is actually this term. So it is okay for you to remember this equation, but okay, in the next notes, I will show you how to prove this polynomial velocity. So it's closely related to the idea of Navier-Stokes equation if you want to use that Navier-Stokes equation, but the same method to prove the this polynomial velocity profile. So for this moment, just please remember that the polynomial means it's actually the power of 2, and then I will explain about another velocity profile. So for the polynomial velocity profile, so we have u over u 2 y over delta minus y over delta square. So might be you may see this kind of equation in our previous chapter, but on that time might be you will have u over u equal to y over h minus y over h by the power of 2. Okay, so because on that situation the thickness is reflect as h, not a delta. But now we assume that the gap, the distance from the local velocity 0 to 99% is delta. Okay, and then we have two major equations, which is shear stress from von Karman. So this is the shear stress from von Karman, and this is the shear stress for the Newtons. Okay, so and then we start with the shear stress from von Karman. Okay, to solve this equation, we have terms of d theta dx. So means this d theta dx mean we need to solve the d theta dx. So it can be d dx for theta. So means we need to calculate what is the value of theta, which is the momentum thickness. So and then we know that the momentum thickness is this one. So we have integration of 0 to delta u over u 1 minus u over u dy. Okay, I think we don't have this square. Yeah. Okay, I'm sorry. So we have u over u, 1 minus u over u. So and then if we substitute the value of u over u here, so we have 2u over u with these terms. So we could get theta is equal to 2 over 15 delta. So I hope you could do this at home. So then what we do, we substitute the value of this theta with the value of 2 delta over 15. So and then we could get these terms. So and we name this equation as equation 1. Okay. And then the second one, we could calculate the shear stress, the tau, using the Newton viscosity law. So we have tau equal mu du dy at y equal to 0. So now means we have u over u of this equation, and then we need to rearrange this equation to become u equal to u y per delta minus u y per delta square. So, and then from this equation, we can get its du dy, and finally we could substitute with y equal to 0. Why? Because we want to make an equation. We want to determine the shear stress at the maximum value. So we have du dy like this one, and then we substitute with y equal to 0, and then we could get these terms, 2u over delta, and then we could say that tau is now equal to, so tau here is now equal to mu du at 2u over delta. And please be careful here, because sometimes student, when it's derived du dy equal y to 0, get 2u over delta here. So this is only the value of this one. If you see the equation for shear stress from Newton, you have a mu here. So means that please make sure that you write tau is equal to mu 2u over delta. And this value is actually only valid if your velocity profile is polynomial, means by the power of 2. Okay, it's in quadratic form. Okay, so means now you have two equations of shear stress, and you could guess what we could do. So we have equation 1, equation 2, and equation 1. So next we equalize both equations. So we have this is the equation from the von Karman, and this is equation from the Newton. So we equalize, and then we let, because we have d delta dx here. So, and then you could imagine, so we could solve the delta by integrating both sides. So, but before that, we need to rearrange the equation. So we do like this one. Okay, I'm sorry. We do like this one. So we have the delta times d delta on the left, and we have all the parameters here in at our right side. So, and then we could simplify this term as 15 mu over rho u dx. So, and then we could integrate both sides. So we could get this one, delta square over 2 equal 15 mu rho u times x plus c. So c is the constant. So we just imagine we need to determine what is the value of c. So how to determine this one? So we need to put the boundary condition. So let's say we have the boundary layer diagram like this one. So normally this one we could take the point at the beginning here. So mean at x equal to 0. So the delta is equal to 0. Then the c is equal to 0. Okay, so and then now we rearrange, because the term here is delta square over 2. So we make it its delta square, and then we could calculate its delta, and you get the final answer of this one as delta is equal 5.48x over square root Reynolds number. So here, at this stage, okay, at this stage, actually, you need to do some tricks. You do a trick to get the Reynolds number, because at this stage, you found that your term is 30 mu x over rho u. So means the Reynolds number is equal to rho u x over mu. So now, if you want to have an x at the bottom, so you need to multiply with x times x. So, and then when you multiply x over x, so you will get mu 30x square mu rho ux. So then you will have the Reynolds number in the terms. So, and then when you square root this one, you will get delta is equal 5.48x over square root Renault. So this is only valid for the quadratic velocity profile. So again, and then I hope you are capable to finalize your equation with a Renault number, because as I said previously, Renault number is used to reflect the velocity, the dimensionless. The Renault number is actually represent the velocity, but in dimensionless terms. So that's why in fluid mechanics, a lot of equation they will use Renault number in their equation. So also in this situation, so it is okay for you to show this one. If you substitute value, you will get the right value of delta. But this is the best equation for delta in Renault number, because you need to represent it in terms of Renault number. Because in all textbook, they will show you the final answer for delta. It's in square root, in Renault number, whether it is square root or Renault number by the power of something. So it depends on the velocity profile. Okay, now you get the Renault number, the delta here. So how to use this delta? So it's quite straightforward. I think you have experience of this one. So for example, we have a flat plate here. So and then we have a boundary layer here. So this is the x-axis. So means that if you want to calculate what is the boundary layer thickness here, so we have a delta. So and then this is at x equals 0.3 meters, for example. And then we have a certain velocity of 5 meters per second, for example. And then you could substitute x equals 0.3 in this x, and then you could get you could calculate the Renault number at this point. So mean you have a Renault number is rho u L over mu. In this situation, we don't use d, we will use the L, and the L here is actually, okay, it can be write as rho u x over mu. So you substitute the x here with 0.3, and then you need to know what is the density and the dynamic viscosity of your fluid. And then you substitute u here. Okay, this is the capital U actually. You need to substitute the u here with the 5 meters per second. So you get the Renault number. So you substitute into this equation. So finally you could get the value of your delta. Okay, that's the idea. So means the thickness of boundary layer is not limited to the trailing edge. You can define at all location of x-axis. Okay, then we start we continue our calculation to get the drag force and also the coefficient of drag. Okay, then we aim to get the drag force. So and then the drag force is closely related to shear stress, because we could calculate the shear stress by tau times dA. So that's why we need to start our calculation to get a drag force with tau. But we have two terms of tau. One is from von Karman and one from the Newton. So I propose to you to use shear stress equation from Newton, because you will have tau equal mu 2u over delta. And this equation is completed, means it is a equation, it's an equation, so and we could use that. But if you want to use von Karman, it's okay, but you need to do some tricks, because okay, so this is the von Karman. So the shear stress from the von Karman is equal to rho u square d over d delta over dx, and then you have 2 over 15. So the shear stress here, the equation is still not complete, because it still have term of d delta dx. You may use this one by replacing the dx here, okay, after you integrate both sides, so means you need to bring x to the left hand side. Okay, you need to rearrange, you need to substitute the value of delta here with this this term, and then you need to integrate it. So then you could find the same final answer. Okay, so means that please make sure that if you want to start to calculate your drag force, please use the shear stress from the Newton, because it is complete. So there is no du dx and so on. So, and then we have the delta here. So we substitute the delta with our previous value. So we have 5.48. So, and finally we get the tau here. Okay. So this is just a tau, means the shear stress, a local shear stress. A local shear stress means if we have plate here, so we have a molecule here, so we are now calculating only one shear stress of one molecule at one specific area, one specific location. Then this shear stress actually will give us local drag coefficient. So local here means the drag coefficient, so mean the dimensionless number that give us the strength of the force, okay, the coefficient. So we call it local because this coefficient is only valid for this specific area. Okay, so and then what we do is we just use this equation. So finally, previously, so I promote to you, I show you that FD can be calculated by using the idea C capital D 1 over 2 rho AU square. So, and then if we equalize that equation with okay, so if we equalize this equation with tau times A, so and then so let's forget about this one first. So if we equalize it with tau and A, which is the force, and then if we cancel the value of A here, means we are focusing about shear stress on a certain location. We could say that tau is actually CD times 1 over 2 rho n U. So here, to differentiate between the local drag coefficient and the total drag coefficient, so we not call it as total drag coefficient, it's just a drag coefficient. So the local drag coefficient and drag coefficient, so we just change this is just to differentiate the symbol. Okay, so I just use the C with a small d. And this term C, D, and so on is actually not fixed. In certain textbooks, they will use C and F. They will say that this is the friction coefficient, and some kind they will skin friction coefficient, and so on and so forth. So I hope you could understand what actually happened on your calculation. So here, so you know from where this equation come from. So, and then if we substitute the value of shear stress that we have, we could calculate the local drag coefficient CD here is 0.73 over square root rho naught. So, and then, okay, the shear stress that we calculated previously is actually about the shear stress that occur at one molecule here. Okay, let's say this is one molecule here, and that's why we don't have any parameter of area. So then, why we cannot just straightforward calculate that one? Because it is not symmetry. So it is not a simple shape. So the boundary layer is like that. So the shear stress here, so is carry certain value, but it's not the same that occur at this location. So mean we cannot just multiple with the area to get the total shear stress. No, we need to do the integral because the strength of the shear stress is different at different location. So what we do is, okay, this is our plate. So and then we take a small area of this one. Okay, So, and then the small area, so you know this is the dx, and the width here is b. Okay, and then we have, let's say we have the shear stress here according to our previous calculation is tau. So means that the force that occur on this area only is tau times A, which is B times dx. And then to get the total shear force and total, this is just the force on this small area. And then to get the total force for the whole plate, we need to integrate this value, and the limit is 0 to L. So what is L? So as showing here, so L is actually the total length of your plate. So this is the x-axis. So we just say that this is the beginning. So it is origin 0, and this is the trailing edge, the last, the end of the plate. So this is will be the L. Okay, so and then we have 0 to L. So we know the value of shear stress here, tau. So we substitute what we have here. So, and then we need to integrate. So one important thing here is, please bear in mind that the terms Reynolds number here is actually consists of x. So we know that Reynolds number is equal to rho Vx over mu. So, and then please expand this term. So, and then when you expand this term, so you have rho ux over mu. Now you could integrate this term with dx. And then you do the integration. And then finally you will get the, okay, here. And finally you will get the drag force is equal to 0.73 u square root rho u mu square root L and B. So this is the total drag force that occur on that plate with quadratic velocity profile. And this is only valid if your boundary layer is 100% laminar. So we talk about that in chapter 5 and 6 when we have 100%, when we could calculate the condition of 100% turbulent or mix between turbulent and laminar. Okay, so so this is the drag force that occur on that plate with quadratic velocity profile. So, and then how to get your coefficient of drag coefficient. So by having this equation, so you have FD is equal CD 1 over 2 rho AU equals by the power of 2 rho AU square. So, and then we rearrange the equation. So we have CD, and then A here is the area. So you know we have a plate like this one. So, and then we need to have this area. So we assume that this is an L and the width is B. So we have L and B. So, and then we substitute in the equation. We substitute the A here, and then we solve the problem, solve the terms, and we will get the CD is equal to 1.46 square root Reynolds. Okay, so that is the way to get the drag force and the drag coefficient from your boundary layers. So mean from your shear stress. Okay, so I give you example for the quadratic here. Okay, however, so normally in laminar boundary layer, we will have this velocity distribution. So we have by the power of 1, which is the linear, and we have the quadratic by the power of 2, we have the by the power of 3, and by the power of 4 here, and then we have the sinusoidal. So this is the very common velocity profile for laminar. So, and then we have another solution which called the Blasius-Isaac solution. Okay, so okay, first I already upload your assignment number 3. So I already upload previously, so you know the assignment 1 and 2, and then I upload your assignment number 3. So asking you to do about the power 3, power 4, and the sinusoidal. Okay, you need to calculate to prove that the delta is equal to this one and the capital D is equal to this one. Okay, so and then you need to prove whether this equation is always fixed or it can be anything. Means that it is okay or not if you write the as, for example, the 7.2 as 7 over 2 y per delta and so on. Okay, so later in previous notes I will show to you. Actually, this velocity profile is actually fixed. Means that if you assume that your boundary layer has a velocity profile of quadratic by the power of 2, so mean this is the velocity profile. You cannot write another profile because it is not fulfill the momentum equation. Means the Navier-Stokes equation. Okay. So now next, I'm going to show you about the Blasius-Isaac solution. So what is the Blasius-Isaac solution? So from Blasius-Isaac solution, so we get delta here. So we have the local drag coefficient is here, and this is the drag coefficient. Okay. So the Blasius-Isaac solution is actually the solution that derived from the Navier-Stokes equation, but I'm not going to show you the derivation. It's very long. So that's I think it's okay not to show that. But the idea that I want to make sure that you know is, okay, previously we are using von Karman equation. So in von Karman equation, we assume that U is equal to capital U. That's why that's what we assume. Okay, so but from the definition of boundary layer thickness, delta, we will take delta as distance of y when u is equal to 0.99 capital U. So means that the von Karman equation actually not using this assumption. So von Karman is actually just simplified the calculation, saying that the u is actually 100% of capital U. So means when small u here exactly 100% or exactly same with the free stream velocity. Okay, but Blasius use the Navier-Stokes equation, then it takes this ratio precisely. So in Blasius solution, Blasius take 99%. It's not take 100% like von Karman. That's why Blasius solution is called an exact solution, because it take 99%. Okay, that's the between the difference between Blasius and von Karman. Then I hope you could remember the equation for the Blasius. With might be the minimum one is the delta and also the CD for Blasius, because Blasius-Isaac solution is the representative solution for laminar boundary layer. So means if your question is not given whether your laminar boundary layers velocity profile is quadratic or sinusoidal or by the power of 3 or 4, so you may assume that your boundary layer, your laminar boundary layer is fulfill the Blasius-Isaac solution. So means you could straightforward use 5x over square root Renault. Okay, so but if your question clearly mentioned that your boundary layer velocity profile is by the power of 4 and so on and so forth, so it means that you need to use specific value of the delta and CD. Okay, so we go for the Blasius-Isaac solution. Okay, so we simplified this one. So the idea is it's come from the Navier-Stokes equation, and it's simplified as f double prime plus 2f triple prime equal to 0. So, and the prime here means the differential. So we have f, and double prime with have d square f over d eta square. We have 2, and triple prime means the d cube f over d eta cube equal to 0. So and then what is f? F is actually the function of velocity in terms of eta. Okay, function of means equation that Blasius developed. So based on the eta, and eta can be referred as this one. So this is the the development of this one is actually based on the Navier-Stokes. So it consists of rho and mu, and or you could replace it with nu. So for this one, so it is okay for you just to remember the step, because this is actually for the analytical analysis. So it is it is very difficult for us to do this on writing exam. Okay, so if I would like to test you about the Blasius exact solution here, maybe, okay, for sure, not maybe, for sure, I must give you a table like this. Okay, why? The Navier-Stokes equation actually, it start to, okay, we have a plate here, so we have the boundary layers. So the Navier-Stokes equation will calculate the velocity for each molecule. So that is the basic idea of what Blasius did. So they will get all the velocity profile here. So that's why we get a lot of data. So and then that's why I say this is just for somebody who want to make do research on boundary layer. So it might be good for them to use the boundary, the Blasius solution for their laminar boundary, for laminar boundary layer. Okay, so this table is actually come from the analytical. So means what is analytical? You just give the value of eta. Okay, for example, you give the eta is actually depend on the y and the x. So mean y and x is actually the coordinates. So mean, for example, you have x equal 1, and then you start to give y equals 0.1, y equals 0.2, 0.3, 0.4, 0.5, 0.6, and so on. And then you could create your own eta. So, and then this data is actually will represent all the coordinates in the in your mesh. Okay, I think a few you have experience, might be do CFD and so on and so forth. So that is the actual what is actually occur in this stage. Okay, to simplify that, okay, for example, you have a table of this one from your experimental, and then you need to determine what is the boundary layer thickness according to the Blasius exact solution. So means that, okay, please remember that, yeah.
Doctor, so the 0.5, 1.0, 1.5 is the value of y, right? Or value of neta?
The value of eta.
Okay.
Okay, x and y is actually the coordinate, the mesh coordinate.
Okay.
Okay. So as you know, the Blasius, the Blasius is called exact solution because it used the idea of y delta is equal y, u equal 0.99 capital U. So it takes the idea of 99%. Okay, 99%. So where we could start these ideas. Okay, according to this table, we assume that f prime mean f prime eta here is actually equal to u over u. So the u over u means the ratio of the local velocity and the free stream velocity. Then Blasius only and to fulfill the idea of Blasius, we need to find parameter on this column, on this u over u column, which is the closest value to the 99%. Okay, you need to understand that you need to choose the closest value to 99%. So the closest value means you have 99% here. Okay, so whether that value is in 98 point something or 99 point something. So mean if you have 98.9 and 99.2, you maybe need to take the 98.9 because the difference is 0.1 compared to the 99.2. Okay, that's what it means. Okay, that's why from here we found that the closest value to the 99% is 0.9916. Okay, because this is the closest value to the 99%. And then when you get 0.9916, so please mark all these row because the calculation will base on this situation, on this data. Okay, and okay, this is the tricks. So for if this question comes out in your final or your test, okay, we must set the answer. Okay, the eta here must be equal to 5. Okay, so this is just to prove the Blasius exact solution. But in a real situation, it means that if you conduct experimental or research on boundary layer, so might be the value here is not, might be it's close to 5, but not, you may have numbers that not exactly 5.0 because this is the, yes, Blasius exact solution, but this is the determination of that boundary layers is actually based on calculation. So it might be a little bit different when we compare to the experimental. Okay. So and then what we do is, okay, we start to calculate the boundary layer thickness. So and then from the table, we assume that y is equal to delta when u is equal to 0.99 capital U, 99% from the free stream velocity. And then from the table, we take assumption that f prime is actually equal to u over u, and it is equal to 99%. And from that row, so we found that f prime is 0.992, where the eta is equal to 5. Now we take the value of 5 here. So we say that eta is equal to 5 and eta is equal to delta. Okay, I'm sorry. Okay, so we take this. So this is the assumption. So eta is equal y per eta is equal to 5, and then it's equal to delta square root u over nu x. So and then we know that Reynolds number is u x over nu. So we could change it as Reynolds number over x is equal u over nu. So and then this finally we could have this one. So and then we replace u over x as Reynolds over x, and then we have Reynolds over x times 1 over x here, and then we could rearrange everything. We could get delta is actually 5x over square root Reynolds. Okay, so here might be you are confusing with this term. So we have the y, u, no x, and here. So here is actually we replace the y here with the delta because we assume that u over u is u is equal 0.99 capital U and y is now delta. That's why we have the equation here, delta. Okay. So that's why in our previous table, we get the delta from the Blasius exact solution is 5x over square root Reynolds number. So this is, and then we continue our calculation. Okay, the idea here is we are not solve Blasius exact solution by integral per se. Means not you need to integrate it according to what equation that you have. You need to solve it according to the table that you have because the data is actually from the analytical. We could say that the data is actually from the experimental world. So we need to get we need to use those data to complete your calculation. Okay. Next, we go for the displacement thickness. So this is the equation of the displacement thickness. So the common equation, but we have problem because this equation is with dy. We don't have any term of dy. We have eta. That means that we need to rearrange this equation to get suit with the idea of eta. So we know eta is y square root u nu x, and then we could have the d eta dy as this one, and then we could rearrange to have dy is equal d eta square root nu x over u. Okay, this is not velocity, this is the kinematic viscosity. So and then we substitute the value of dy here with this one. So and then we substitute the 1 over u here with f prime, because this is the first assumption we made. Okay, so and then we need to change the limit. So the limit is not 0 to 5 anymore. So we need to change into 0. The limit is not 0 to delta. So the limit, because we do our integration in terms of eta. And according to the table, so the limit is from 0 to 5.0. So means now the limit is 0 to 5. So and then we solve this one, okay, because it is only the integration is to d eta, so we could bring the constant value outside. So and then we have integral of 1 eta, so we have an eta. So and then we have integral of f prime d eta, and then integration of f prime mean, I think you know this one, the integral of du dy. So it will have complete integral of du, so you will get the u. It's come back to its own terms. Okay, so and then so we will have this one. So we have integrate this one. We have eta, and the limit is 5 to 0. So we have integral this f prime. So it will become only f. F mean f in term of eta. So this f prime also f prime in term of eta. Now the prime is disappear because we integrate the differential form. So we have f eta with limit 5 to 0. So here, okay, please have this value according to the table. So for this one, it is okay for you because we are integrating eta from 0 to 5. So mean we substitute the 5 here and we minus with 0, so we get 5. But for this one, you must take from the table. Okay, let's say we are now take 5 to 0 and f eta, and we're looking back to our table. So we have our f eta here. So when f eta is 5, so we get 3.28. And when if eta is 0, so we get a 0 value. So mean the total value is 3.2 minus 0. 3.2 here and minus with 0. So that's why we could get a value of 3.2834. Because this value is actually the value of when you substitute the value of f at eta equal to 5 minus with f at eta equal to 0. So and then you could yes.
For the delta star, right?
Yes.
The displacement thickness.
Yes.
Why the 0 to the delta is 0 to 5? I thought neta is 0 to 5, but the delta is not 5.
The delta is not.
You see the yeah, this one, yes.
Okay, so here we limit to this one. Okay, so this equation is based on y-axis. Okay, previously that I explained to you. So this is y-axis. So when the u is equal to 99%, so u here, y here is equal to delta. That's why we take limit from 0 to delta. Okay.
Okay.
Okay. Now, problems in Blasius solution, they don't use u over u directly, so they don't use y-axis directly. So they use something else, which is eta. Okay, because they have the equation here and simplify this equation in eta. So means that we cannot integrate this form in to dy because we have eta now. So we need to rearrange the equation first.
Okay.
Okay, so we rearrange the dy by using this idea, and then it's become d eta u nu x over u. Okay, I hope you understand this one. Is that
Oh,
okay?
yeah.
Okay, and then we replace the u over u with f prime. Okay, that's clear. So and
Okay.
then, so this limit is actually 0 to delta based on this diagram.
Uh-huh. Yeah.
Okay, so that's why we have limit 0 to delta. But when we change our equation into d eta, so we need to change our limit too. We need to change the limit too because we change everything. So we need to change the limit. So the limit here is, okay, why we take delta? Because when y is at y at u equal to 0, u equal to 99% capital U, y is equal to delta. So now eta. So
Yeah.
eta means if eta reach the boundary layer thickness, okay, so the dy here, okay, so the value of eta is 5.
Yeah.
Okay,
Okay.
can you get it?
Yep, get it. Thank you.
Okay, so that's why we change the limit from 0 to 5.0.
Okay, thank you.
And then you could solve it, but please make sure that you solve based on the table that you have. And this table is actually not worth to remember the value here because it might be different from another table to another table. For example, in another textbook, might be they will give you only 0, 1, 2, 3, and 5. For 1, 2, 3, 4, 5. Another textbook, they will give you a little bit specific, might be 0 0.1, 0, 0 0.2, 0 0.4, and so on and so forth. Okay, so might be the value here is a little bit fluctuate, depends on how many, the precision that you put in your eta here. Okay, so and then if you calculate, you could get this one. And then previously from the idea of we know that delta is 5x over square root d naught, or from this one, okay, this is the previous, okay, not this one, I'm sorry, not d naught number. So from this equation, I think you see this equation in the first solution. Okay, so and then we substitute into, we could change into delta over 5 as square root nu x over u. We substitute it here, and finally we could say that the delta star is equal of this term. So and then we substitute the value of delta. So and then we could say that the delta star is 1.7166x over square root of real number. So then, so this is the calculation of momentum thickness. So we have this one again. So need, because this is the equation that comes from the x and y coordinates. So we replace the dy as this one. So we replace the u over u as this one, and then we bring out the constant value because this integral is only for the eta. So we bring this is the value outside. So we bring it here, and now we need to solve this one. And again, bear in mind that in Blasius we are solving problem based on calculation table, based on that table. So means we need to do this according to value that we have in the table. So we rearrange the equation. So the integral here means the summation. I think you could understand. So the integral is actually need to calculate all the value in a certain range. So means that we could replace it with the idea of sigma, mean the total value for certain item. And then we have f prime 1 minus f prime, and we have d eta. So d eta means delta eta. Okay, and then this calculation need to be done according to the table. So how to do this? Okay, let's say. So according to this equation, so we have d eta, we have f prime, and we have 1 minus f prime. So, and then we could create table. So we have eta here, we have f prime, and we have f1 minus f prime and times delta eta. So f prime minus f prime time 1 minus f prime is actually the operation that you do based on this value. So you have this value, and then you have 1 minus f prime, so you need to do 1 minus this value, and then you multiply that two value, and d eta here means the interval difference. So the delta eta here is 0.5. So you calculate everything, and then you will get these numbers. Okay, so from where you get the f prime here, so it's actually from this table. So you have f prime here, so you have this table. So you take all this table, and then you could start your calculation. Okay, so this is the value. So, and then if you get everything here, okay, you start to calculate, and then please remember that we have sigma. Sigma means the summation. So what you need to do is you need to sum all these values, and you will get this term, this value 0.6548. So, and then you could continue your calculation. So I mean you have a delta over 5. So I hope you could understand this one. Okay, we just replace this one with the delta over 5. Okay, you could refer to the previous step. Okay, and then we could replace this term into these numbers according to what we calculated based on that table. And then we substitute the value of 5x. So finally we get theta is equal to 0.6548x over square root, we know. And if you check these numbers, okay, it is actually different from the official value of Blasius numbers. Okay, the official value is 0.664x over square root. You know, this is the when you open textbook or you search in internet, they will give you this is the theta for the Blasius solution. Why? Because our table is not details enough. So that's why we get a little bit different in terms of numbers here. So so means that if you need to get the Blasius, so you need to have a very detailed table, so you could have you could calculate precisely. Okay, now we calculate the same things. We start to calculate the shear stress, and then we could get the drag force, and then we could get the coefficient of drag. So okay, so we start with this. Okay, let's say we have u over u is equal to f prime. Okay, so I'm sorry, this is not a small eta. So you should write this one as f prime eta. Okay, not the superscript terms. Okay, so you have u over u df d eta, and then you could rearrange this by having f prime, okay, or u equal capital U f prime. So, and then if we do du d eta, so we have u df prime like this one. Okay, so this is, I think you already know. So we don't have d here. So when we differentiate the u here, du d eta, so the f here will become in differential form too. So the u will be constant because u here is the free stream velocity. So free stream velocity is not changed. Okay, and then this is also we get from the table, from the assumption of Blasius. Okay, we could have a d eta dy with a square root u over nu x. So I think this is we previously could have this one. Okay, so we have this one previously. So refer back to von Karman step. So to the shear stress is actually calculated from the shear stress equation. One is von Karman and one is Newton's. So but for von Karman, as I said, the term is not complete yet because it has d theta over dx. So that's why you are advised to calculate the shear stress by using the Newton, because the Newton is quite easy to solve because they just use this term mu. It just use the term of tau mu du dy at y equal to 0. So and then why we do this? Because we actually have problem to solve du dy here. Okay, because in Blasius we don't have exactly u over u terms, so we need to do a little bit modification. So we just write du d theta here, du d theta, and d theta dy to get du dy, because you know we could cancel this d theta to get the du dy value. So and then we substitute the the value here. Okay, so we have this value and this value, and then at y equal to 0, eta also equal to 0. So we just replace the y equal to 0, become eta equal to 0. So and then if we solve it, okay, so mean that tau here is mu u square u over nu x square root u, and we have here df at eta equal to 0. Okay, so this is you should know that df prime here means it is equal to, so it is equal to d over f prime. So f prime here is d of f df over d eta. Okay, so means that the differential here is 2 times. So we could replace the df prime here with f double prime. So now we need to calculate what is the value of f double prime at eta equal to 0. So here we could say that we cannot solve this one by mathematical, but we still need to refer the table. So we refer to the table y eta equal to 0 for f double prime. So if we see this one, we see the table here. So this is f double prime for eta, and at eta equal to 0, the value is 0.3321. So then we substitute the value here. So we substitute the value of 0.3321, so we could get this is the tau for this for Blasius condition. Okay. So and then we calculate the local coefficient CD here. Okay, and then we could get I can make it faster a little bit. So we have tau over 1 over 2 rho u square. We substitute the value of tau that we get from a previous calculation. Now we get the value of CD as this one. Okay, so we go for the drag coefficient. So the drag coefficient is CD is equal to FD over 1 over 2 rho u square and A. And A here can be substituted with B times L. So I hope you could understand the B and L. B is the width and L is the length of the plate. So and then so we substitute that one. So this is just to I solve it from another point of view to give you another equation. So so the tau here is now replaced with the von Karman. So we have the von Karman equation of shear stress, rho u square d theta dx. Okay, and then we could neglect the value of dx here. So we have d theta. We could neglect the value of rho u square here, and we could neglect the value of b. So now we have integral of d theta over 1 over 2 times L, and integral of d theta mean integral of 1 d theta. So you will get theta. So and then you will get, you bring the 1 over 2 up there. So you will have the CD is actually can be calculated by multiple U with theta and L. So this is the another equation for you to calculate the drag coefficient for laminar boundary layer, whether it is Blasius condition, Blasius solution, or with a certain velocity profile. So mean if you want to test, for example, you take the velocity profile U over U in quadratic, for example, you find the value of theta, substitute with this one, and finally you could get its drag coefficient. So in previous calculation, we get the theta is 0.6548x square root Renault. So we substitute into this one, and then we could get these terms. So bear in mind here, the L here is actually the x. So you could assume that L here is equal to x because both of these terms is actually represent the length of the plate. So you will have this one, okay, and then you will substitute, you will get the value of CD is equal of this. And again, okay, if you see the official value of theta is actually 0.664x square root Renault, and means that if you substitute the in previous equation of this one, okay, you will get the CD is 1.328 over square root Renault. This is the official value of CD of Blasius solution. Okay, that is the idea of a boundary layer, of laminar boundary layer, because we still have the separation, we still have the turbulence and so on and so forth. So it means that both, you know both the Blasius condition and also the von Karman assumption solution. You know how to calculate the boundary layer thickness, you know how to calculate the CD and the drag force.